So the first type of magnetoresistance we're going to study is called an isotropic magnetoresistance.
AMR based?
AMR.
Okay.
Okay. So this was this kind of phenomenon was reported back in the 1800s by a British physicist.
Yeah, Lord Kelvin?
Lord Kelvin. Yes, correct.
Amazing.
So it was long time ago, right?
Amazing.
So what is this anisotropic magnetoresistance? Now imagine you have a very thin ferromagnetic material, like you see here, this blue part here.
Yeah.
Okay. Now this could be an alloy of iron, nickel, or some other material. Okay. Now if you connect a voltage plus or minus, this what's going to happen?
There will be some current.
There will be some current flow, and then there will be some initial resistance, right? Which is
that's the R0.
R0. Okay. Now, what happens now when you apply a magnetic field to this material? Now there's thin ferromagnetic material. You apply a voltage, so there's a current flow. Now you apply a magnetic field.
So,
what do you think might happen? I mean, looking at the name and also this material and the current,
resistance will change.
Resistance will change. Okay. But
why is it changing?
Why is it changing and how is it changing? Now, is it if you apply the magnetic field in any kind of direction, will the change of resistance be the same? Or let's say you apply magnetic field this way, and let's say you apply magnetic field this way. Or let's say another field in between.
Okay.
Do you think this resistance change will be the same? Or do you think it might be different due to some phenomenon?
I don't know, but from the way you are saying, it seems it has some dependence.
So, in fact, the the change in resistance, right, is a factor between the current and the angle of the magnetization.
Okay.
Okay. So what they found out was this is due to something called electron spin dynamics and scattering. We'll touch on that very lightly, briefly. I don't think it's out of scope of this course to study about spin scattering and all those things, but it is due to that. Now, what they found out was that electrons, because now there's a current flow. You said there's a current flow.
Yeah.
They seem to scatter more when the magnetization is parallel to the current.
Okay.
Right? And this scattering is lowest when the magnetization is somehow
90
degrees.
Okay.
Right? So that's what they found out. So here, if you look at this equation, right, R0 plus del R cos squared theta. Now, if you draw a graph, right, this is your resistance. This is the angle between the current and the magnetization. What you'll notice is that when it's parallel, so magnetization then is parallel to the current, right?
Then the resistance is maximum,
right? Because the electrons scatter more. Now, if you slowly if you slowly change the direction of the magnetic field, right? As you see here, let's say you move it now to 45 degrees.
Okay. Then it's increasing. Or then the resistance is decreasing.
Resistance decreases. Okay, now, then you also have a minimum resistance where it doesn't go below that when the magnetization is
90 degrees.
Right? So here, this change in magnetic field, right? It's nothing to do with the amplitude of the magnetic field. It's here what we are...
it can be smaller or higher, is it?
Yes. Generally, because we are talking about the angle between the magnetization direction and the current. Okay. So, what kind of applications do you think this kind of magnetoresistance can be used?
So the direction of the external magnetic field or the field that the sensor is exposed to, has to change. That direction has to change.
Yes.
That is what we can say.
Yes. That's what. And if you look at this graph, right? There's also two things. One is there's a linear region. Yeah.
Yeah. That looks somewhat linear.
Somewhat linear. Plus, What else do you see in this graph? Can we, for example, accurately measure
Direction?
125 degrees Celsius with this scale of
120 degrees?
Yeah.
I see it.
Or can you measure, can you, for example, say minus 45 and 45?
No, they are same resistance values.
There's symmetry.
Yeah.
No, yes. Right? So that their range is then limited to 90 degrees.
Yeah.
Because it measures the same resistance value.
Yeah.
Even if you angle, but based on that, you cannot tell because this type of material isn't able to identify the north and south poles. That's right. It's the same.
The direction of the field you cannot.
Direction of the field, yes, you cannot. Only the angle between the direction.
But for a limited range of angle, it's almost a straight line.
Yeah, maybe no, up to what, minus 45 degrees or plus or minus 45 degrees. It seems to be somewhat linear.
Or I would say, I mean, not close to zero because that region is around
flat.
Correct. So maybe from 20 degrees for sure
to what?
To 60. Yeah, depends on the
So, what kind of applications? So differently, based on what we've seen, you can say it's kind of a natural angle sensor, right? Because the output changes according to the angle.
Correct.
So it's used in a lot of.
But I saw a cos square term.
Sorry,
it's a cos
squared theta.
Yeah. Yes. Still, it's linear for some region.
Yes.
Yeah.
Because still, it's depends on the angle, right?
Yes.
So you basically are squaring that.
Correct.
So so because it's a natural angle sensor, it's used in a lot of automotive applications. Motor rotor positioning, steering wheel angles, on-off switches.
So you attach a permanent magnet to whatever component it is rotating.
Yeah. You have your shaft. Let's say your shaft is rotating.
So the shaft is rotating. You want to find out the angle. We will attach this permanent magnet to that.
Yes. So let's say you attach a dipolar magnet here, right?
And then
south. And then you have an AMR element underneath.
Sensing that magnetic field direction.
Yes. So here, for example, you can see it's the same thing here, right? So here, the magnetic field is parallel to the current. And here, when you rotate, it becomes
outline. Yeah.
Right? So you get a graph like this. If you draw the resistance and the angle, you'll get something like this. Yes. Which is what we saw
for 1 degree, 0 to
360. But between 0 and 360, you can see it repeats every. Well, this is 180, right? Comes out every 180 kind of repeats. And even between here and here, your resistance change will be the same. So you won't be able to see actual angle.
Yes.
Another way is to use them as if you want, let's say a car lock or your door handle or something like this. You can have your magnetoresistance sensor here, and then you can have another dipolar magnet. Now, if you move this,
then it's your maximum or otherwise minimum.
So, but this is kind of an on-off kind of signal. So that's another way of using this AMR sensor. So a lot of different automotive.
See, you mentioned this R naught or R max, etc. What is the typical values?
That's a difficult question.
But is it large?
I don't think it's large. I'm saying that based on my knowledge of GMR. But with AMR, I actually do not have typical values for that. Yeah.
But it is good to have large values so that maybe the power loss, etc. will be less. Because to measure the resistance, you have to give some. Finally, it is you will need a circuit to measure the change in resistance.
Yes, large. I mean, you're probably, when you mean large, you're probably talking about like kilo orbs. Yes. That's what I'm talking about.
Yeah.
That for me is, not mega or
Yeah.
high. Yes. So that's what I was thinking. Maybe it's in that range.
Yeah, because when we talked about the strain gauges, it was like 350 ohm.
Yes.
Things like that.
Which is pretty small.
Yeah, it's in the ohm range, but this will be much
higher. Oh, yeah. So it will be much higher than, let's say, 10 or 20 ohm.
So the associated power loss will also be less for the measuring circuit.
Yes, because remember, you also have to give a current.
Yes.
To the material, right?
Yeah.
It just doesn't change its resistance on the current.
Correct.
Right? Now we had a look at how it's used connected to a magnet like this. You can also measure linear displacement with a magnet like this. But for that, you need to somehow have the dipole magnet, the center of the dipole magnet, and the same center of the
sensor.
Also, this distance should be about half the distance of the magnet.
Okay.
So from what I can gather, how this works is, let's say you have something like this. Now, if you have these fields, right? That is a very bad picture. If you have this field. Now, this field direction is changing, right? Of this, correct? Now, when you move this, I guess
the angle of the field is okay. Got it.
Right. So then, when you move up and down, so here, for example, you could have in the car, you have your pedal up and down. So maybe something like this could be used to measure that angle. Yeah. What about here, Bobby?
This rotation. So this will give maybe some pulses in the sense north, south, I can see.
It will give you some pulses, but also before we saw, you could probably measure up to
some degrees.
Yeah, so here you can go up to 180 degrees.
Correct.
But here you have 1, 2, 3, 4, 5. No, 1, 2, 3, 4.
Yeah.
4 dipolar magnets.
Correct.
So then the range will be limited to 45 because it's repeating.
Yes.
Right?
Yes.
So the more number of magnets you have, the lower this value will be. This range will be. Right? Because it will then reset to the...
So if it is keep on rotating, I mean, one rotation may give a series of change in resistance.
Yes.
So I may get 8 pulses or something.
Yes. Depending on the number of magnets you have. Yeah. But that angular range will get smaller and smaller, like this. So this, I'm not sure. Again, any kind of rotating improvement maybe. But it's not exactly to measure the angle though, right?
Yeah, I think it is to measure the rotation. The RPM, etc.
The speed. So some examples of that. Okay. Now, there are a few things we've seen here before. We've seen the bit circuit.
Yeah.
Now, generally, these kind of magnetoresistive elements, right, are arranged in a bridge circuit. Okay. Plus, in the example we saw,
so all these 4 are magnetoresistive, or
all these 4 are magnetoresistive elements
in this diagram.
Yes. Now, then the question is,
I see some pattern also.
Why do you think there's a meander pattern here? I mean, we call this a meander pattern, right? It's meandering. And we did this for one of the courses. The
strain gauge,
right? But in this case, why would you have the magnetoresistive element, which is this one's here? Why would you have it in kind of a meander arrangement? What's the reason for that?
to get more sensitivity in one direction?
Yes. Perfect. To get a well-defined orientation of sensitivity. And that's another reason. And you just talked about that just before.
You want larger value of resistance in a given.
Well, you're on fire today. You're on fire today. Exactly. Yeah.
Given area, I wanted to achieve more resistance. Okay.
Yeah. We have a larger. Yeah. Now, so here, let's say this is R1. I mean, according to this. See, R4. Okay. Now, let's say I apply a magnetic field in this direction. Here.
Yeah.
What's going to happen now?
So for the red and blue, it will be, I mean, they both will give different, or they both will have different sensitivity to that direction of the field.
Yes. So here and here,
same.
And the resistance will decrease. But here, it's parallel to this.
It will increase.
So here, you get some output.
Correct?
Yeah.
So we can form a full bridge.
Yes. So this one and this one is changing.
Yeah.
Same. And this one is changing the same. Correct?
Yes.
So we'll get some. I mean, we did bridge circuits. So
yes.
We don't need to do that. But correct. But for this, let's say for this arrangement, we will get an output.
Yeah.
Okay. Arrangement 1.
Yeah.
Now, let's say I change. Now, this was the original.
Yeah.
Now I change it to 45 degrees.
Yeah.
Then what's going to happen?
45 degrees.
Yes.
Then all will have same sensitivity or same output, same change in resistance.
What would the output be?
0.
Now, I change magnetic field to 90 degrees again. Then
red,
this way.
Yeah, the reds will have higher resistance compared to the blue ones.
The reds will have higher resistance compared to blue ones.
Yeah.
Correct. So then you will get an out.
Correct.
So we started with 0 degrees. No, we started with 0, no? 0. Then we went to 45 degrees. Then we went to 90 degrees. Now what's going to happen if we go to the other side? Same. What does that tell you?
You can operate only in this range.
Yes.
Otherwise, you cannot resolve whether it is 120 degree or...
Yes. That means with this kind of setup, with the magnetic elements arranged in a bridge circuit like this, your maximum range is 90 degrees. Now, what if you... But it seems like a pretty
After that range. Also it is changing, but there is a symmetry, like you have mentioned.
Yes. So after it is changing, but we won't be able to tell the exact angle.
Yes.
Right? So 135 could be 45.
Yeah, correct. 90 plus or minus theta is the same.
It's the same.
Yeah.
So then, so the maximum range we can accurately...
or we can resolve.
Yes. Right? For an angle is 90.
Only for this range.
Now, is there a way to somehow increase this?
Increase the range?
Increase the range. Oh, by the way, sorry. Another thing I forgot to mention here.
Mm-hmm.
Now, this is an op-amp, no? But what if you have something like a comparator? Then what is the output going to be like?
It will be just high or low.
So again, this...
It will say above 45 degree or below 45 degree.
Yeah. So again, if you have something that you want switched on and off.
Yeah.
Right?
Correct.
According to the angle of the magnetization.
It can be used.
Yes.
Otherwise, we will be using some difference amplifier or instrumentation amplifier to measure the difference output volt.
Yes. And based on that, you can...
How much angle it is.
Yeah. But I mean, for me, I want something that can measure more than 90 degrees. For me, this seems like it's not a very good option. It is nice, but I want something. Measure. I have a new application.
Increase the range.
Increase the range. How can you do that?
Oh. You have two of them.
So.
Okay. And then they are in series. No. So one will sense for some range, the other one will sense for the other range. Is it?
Boby, I'm telling you. What did you eat today?
I had a coffee before that class.
Yes, that is correct. Because somehow we need to know when it's on the other side.
Got it.
Okay, so how do we do that? So now, let's use our example that we did before, right? So what do we see here? First of all, we see two things, right?
Yeah.
One is that there you have your bridge circuit that we saw before.
So the correct.
And this is rotated 45 degrees.
It's like shifted by 45 degrees.
Yes. Shifted maybe, huh?
Yeah.
This one.
Yeah. It's like an offset angle that you have introduced.
Yes. Somehow I mean, we can easily do that, right?
Yes.
Now let's say you apply a magnetic field as you did before in this direction.
Yeah.
Okay. Then we know
We get the same.
We
discussed.
Yes. But then what about here?
So that will be 0 now.
This will be 0.
Because we have seen that 45, the output is 0 for the previous configuration.
Yes. So here, now, let's say
maximum.
You have a maximum gap. Now because of this, we have
the other one is at 0.
This one is at 0. You do your 45 degrees now.
That becomes 0.
This becomes 0, right?
But the other one is at peak. Okay. So you are getting sine and cosine waveform.
You are getting sine and cosine waveforms. Fine. But then...
So now you will be able to resolve till 180 degree, I think.
But how? I mean, okay, so you have a sine waveform here
and
a cosine waveform.
Yeah.
Okay, fine. So you have two waveforms.
Correct.
But then how can you resolve which angle that you're measuring?
So I can see if the 45 degree shifted one is positive, then I know it is between 0 to 180 degree.
Say that again. If the shifted one is
giving a positive output.
So that means sine wave.
Yeah.
Sine wave is giving a positive out here, for example.
Yeah.
And
so it is positive for the 90 degree.
This one?
No,
this is 45 degree.
45 degree. No, it is positive till 90 degree. No?
Positive till 90 degree. Yes.
Yeah.
Yes.
Yeah. Correct. So if that is positive, then I know we are in the 0 to 90 degree range.
Here to here.
Yeah.
Okay. Fine. Now?
So at that time, whatever output I get for the original or the first bridge can be used as the angle measurement output.
You mean this? This is cos, no?
Yes.
This is sine.
Yeah.
First bridge means this bridge.
Yes.
And then now if I go this...
No, wait. See, you have a waveform starting from maximum to minimum.
Yes, cosine wave.
Cosine waveform.
Yes.
So each value corresponds to certain angle.
Each value corresponds. Yes, correct.
Yes. So our confusion was, is it below 90 or above 90?
Yes.
Now, the bottom bridge gives a positive output till 90 degree.
Yes.
Then it gives a negative output 90 to 180.
Yes.
So I am now able to distinguish whether I am below 90 or above 90.
Okay. Based on that first bridge.
Yes. Or second bridge. Shifted by 90 bridge.
based on this one.
Yes.
So there's a
Yes.
so
that could be a solution.
In fact, you're right. So you do look at sine and the cosine rate, but they have an equation based on arctan.
Yes.
Right. And this is what you were talking about, I think. Oh, this is what you're trying to explain, I think.
Yeah. I mean, this theta can be calculated this way.
Yes.
Or otherwise, we can look at this way also.
Yes.
Because the previous one, we were struggling to know whether it is above 90 or below 90.
Yes, because both are the same.
Correct.
Right.
Now,
We just have the cost.
From the second one, I know whether it is below or above 90.
Yes. So based on that, you should be able to figure out which way you're going, right? So again, there's also an equation for this, right? So the other way is obviously, again, very easy. So this mechanical angle, right? And you have a measured angle, right? So there's the difference is the mechanical angle is the object or whatever you're changing, right? The measured angle is what the sensor measures.
Correct.
Right? So we should not confuse that mechanical angle.
Because the sensor can measure only from 90 to minus.
Exactly.
Okay.
Right.
Okay.
The mechanical angle can
it can be keep on rotating, so the angle will
right.
add to, yeah.
Right. So then if you have for example, let's say you choose this one, which is more than 90, no? 135. So in this case, what do you have here? Two things, no?
Yeah.
So here, this is, let's say, y and x, because it's arctan y over x, y and x. Now here, 135, now we've gone beyond 90, correct? Here, we have what? A positive sign.
Yeah.
So?
Positive or negative?
Oh, sorry.
Sign is negative. Yeah.
So, y is less than 0.
Correct.
X is what?
0.
0. So, y is less than 0. X is 0. Then?
Minus
degrees.
5. Yeah.
Minus 90 divided by 2 is minus 45. Which is what you see here.
Okay.
Right? Similarly, for the students, just to give another example, let's say another random one. Let's say take 225.
Also, you went beyond 180.
Now we are gone beyond 1. But what do you see here though? There is a range now is between 90 and 270. Let's say if you go beyond that, right? Then that range is now doubled. Now we have a 180 degrees range and we can clearly measure if it's minus or plus.
Yeah.
So if you take, for example, 225, same thing. What is this value? So we have, wait, have to draw a straight line. I think at 180, this is 0, which is your cos.
Yeah.
Your x is 0.
Yeah.
So x is 0. And then y is more than 0.
Positively, yes.
So x is 0, y is more than 0, then that means it's 90 degrees divided by 2, 45 degrees, which is what you measure here. Okay. Right. So based on that, by having two bridge circuits, one is 45 degrees.
So what is the maximum range it can have now? 180 degrees.
180.
Not 360 yet.
No. Actually, I don't know if you can do 360. Maybe you need more bridges.
Yeah, with this it may not be possible.
With the two bridges, no.
Yeah.
With more bridges, maybe, but in fact, I have not seen, because I checked a lot of the companies that do these AMR sensors. And most of them, so this is, I think, analog devices. So they have the bridge sensors 45 degrees, shifted 45 degrees. And they have, sine outputs and cosine outputs here. So you ask the question, can it go 360? It cannot, because see, this is your mechanical movement.
Yeah.
You're going to 360, but then after 180, it drops down, right? So for each full circle, you can get, it goes up and down twice.
Yeah. So somehow 90 degree we have extended to 180.
Yes. And I think in most cases, now I'm trying to think of other cases, in most,
Depending on the application.
right? In most applications, it goes only 180.
Yeah.
I mean, if you look at automotive applications.
Yeah. But if it's a steering wheel, it can be more.
So steering wheel, I was actually thinking the other day. Steering wheel normally go like this, no? Don't go like, I'm not going to turn it, no?
Yes, you turn it.
In this case, yeah, this is true. But in that case, maybe the car knows. Somehow.
This sensor cannot be used.
This sensor cannot be used. And there are, I mean, yeah.
There are.
So AMR cannot be used.
I mean, you may need one more unit to know whether you are above 180 or below 180.
That's true. Yeah, but I haven't seen that. So maybe this is for most applications. Maybe you will need.
Also, sometimes I see designs using gears. You reduce this rotation to, lower angle, and then you measure.
Oh, okay. Really? So that is then reduced to 360 degrees to. Oh, okay. Okay.
But there are specific steering wheel sensors. Because steering wheel sensor, here we have used a magnet on an axle. Correct?
Yes.
You have a shaft and you have attached a magnet.
Yes.
That kind of structure is not usually possible for the steering wheel. Because steering wheel has got a rod.
Yeah.
You cannot attach a magnet at its center.
No, that's true.
Yes. So it requires a different design idea.
Yeah, you cannot just add. Yeah.
Yes.
That will not work. Yeah. But nevertheless, it is still used in, a lot of automotive.
Yes, that's a lot of applications.
Yes.